Thank you very much for attending our presentation today. My name is Henrik Olsson, and here with me is the co-author Kevin Ross, and in attendance is our professor Jingchen Monika Hu. So as a quick note before we start our presentation, we do want to say that we actually presented at the privacy and statistical databases before this, and we had the opportunity to extend the research from our paper. And so the presentation that we'll be discussing today is actually our research topic in a little bit of a more detail. So without further ado, today we'll be talking about the two-phase data synthesis for income and application to the National Health Interview Survey. So as a brief introduction, Kevin and I were in a Bayesian data confidentiality senior seminar in our undergraduate studies at Vassar College. And in this seminar, we actually completed a project where we applied our learnings in Bayesian data confidentiality and created synthesis models. As we were looking through public data sets, we found that many variables such as income were highly sensitive due to issues of skewness and point mass at zero. And so we decided to apply our synthesis model to the National Health Interview Survey, which consists of socioeconomic, health, and demographic variables. Then we implemented a two-phase synthesis process to preserve variable relationships as well as protect the privacy of the individuals in the survey. Then, in order to assess the effectiveness of our synthesis model, we assessed the utility evaluations as well as the identification and attribute disclosure risks. Specifically looking into the variables that we chose, first we have our response variable, which is income, and we split it up into a binary and continuous form. As we see from the table below, we see that income B for binary is either 0 for zero income or 1 for non-zero income. And then income C for continuous is 1 to 149,000, where it is top-coded. And then we selected 7 predictive variables, which includes 2 continuous variables, age and hours worked, and then categorical variables, sex, race, education, health insurance, and home ownership. So diving into our two-phase synthesis model, the first phase, we synthesize the binary income. This is a similar two-phase approach as used to impute missing data. So we use a Bayesian logistic regression model with random variable yi, which is the outcome of income B of record I, and yi is either 0 or 1 in this case, which follows a Bernoulli distribution with pi as the probability of yi equaling 1. And the logit of pi is the linear combination of the main effects of all 7 predictors. So step by step, we first specify a normal prior for each beta I, and then we perform MC estimation with all observations. And in our case, we had a total of 5,000 observations to collect the posterior draws. Then we use the posterior draws to simulate M synthetic income B values. Then in phase 2, we synthesize the continuous income using a Bayesian linear regression model. And in this case, we have random variable zi, which is the log outcome of income C of record I. And this follows a normal distribution with mean mu I and standard deviation sigma, where mu I is a linear combination of the main effect of all 7 predictors. Similar to the first phase, we first specify a gamma prior for the inverse of sigma squared, and then proceed to do MC estimation with only the non-zero income observations that we collected from phase 1 to collect the posterior draws. Then finally, we use the posterior draws to simulate M synthetic income C values. And then the final step in our two-phase synthesis model is that we combine and then transform the income B and income C synthetic values. In order to assess how effective our two-phase synthesis model was, we compared it to a single-phase synthesis where we specifically synthesized income from a linear regression model. However, there are a couple drawbacks. First, there's no specific modeling of the point mass of zero income. And second, there's a possibility of not generating any zeros. So, as a summary, our two-phase synthesis model uses both the binary and continuous income, while in the single phase, we only look at the original continuous income. And then in the two phase, we use both a logistic and linear regression model, while in the single phase, we only use a linear regression model. And so next, Kevin Ross will be speaking towards the utility evaluations.
Right, so first the utility evaluation, and specifically the density plots of the marginal distributions. We display here the original data of income, the two-phase synthesized income, and the single-phase synthesized income with the embedded violin plots. The two-phase and single-phase are randomly selected from one of 20 synthetic datasets. However, they all look fairly similar to what you see here. And then across all three, we see that the means are relatively similar. However, the 25th and 75th percentiles, along with the extreme values, are a lot more similar between the two-phase and the original data than the single phase in the original data, indicating that the two phase had a slightly higher utility. Next, we measure the propensity score in empirical CDF. And first, the propensity score is simply the degree of ability to distinguish original and synthetic data sets. The propensity score is a classification algorithm, and to do that, we use logistic regression on income, regressed on all available predictors. A higher score here indicates a lower level of similarity and thus a lower level of utility. And we see that the single phase has a slightly higher propensity score than the two phase, indicating that the two phase has a high level of utility. For the empirical CDF, that's just the differences in empirical distribution functions measured from the original and synthetic data sets. And in this case, we measured it both with the maximum absolute difference and the average squared difference. And similar to the propensity score, a lower value here indicates a higher level of similarity and thus a higher level of utility, which we see reflected in the two-phase measurements for both cases. Our next utility evaluation are the confidence intervals and interval overlap, specifically for mean and the regression coefficient of age. For mean, we see that the point, or actually the 95% confidence interval overlap measure, a higher value closer to 1 indicates that the intervals were more similar. And we see that it's in the case with the two-phase has a lot higher interval overlap compared to the original than that of the single phase, indicating a higher level of utility. And we see a similar case in the regression coefficient where with the interval overlap for the two-phase, 95% confidence interval overlaps higher than that of the single phase. And we like to note that the income was slightly skewed, so regression may not be the best fit here, but we still decided to include it anyway. Next, we measured the risk evaluations, starting with identification disclosure. And identification disclosure is the risk of an intruder correctly identifying targeted records in synthetic data and learning sensitive information. To do this, we assumed the variables sex, race, and education were known by the intruder, and we assumed a match if the guessed income was within an interval of radius 30% from the true income values. To quantify this, we calculate the expected match risk, which is the probability of performing a correct identity match, the true match rate, which is a percentage of percentage of true and unique matches, and the false match rate, which is a percentage of false and unique matches. The expected match risk and the true match rate both fall between 0 and 1, and a lower value here indicates a lower identification disclosure risk. And the false match rate is also falling between 0 and 1. However, a higher value indicates a lower risk. And we see that from the table below that the two-phase for the expected match risk has a slightly higher value than that of the single phase, indicating a higher level of risk for the two-phase synthesis. And our final risk evaluation measure was attribute disclosure, where attribute disclosure is where the intruder can correctly infer the true values of the synthesized variables. And so we calculate this probability for correctly inferring the true income value for each record. This calculated probability is simply the normalized attribute disclosure probability of the true value among the 11 records, where 10 neighborhood records plus the record itself. And as an example, for the true income being 10,000, with increments of 500, the neighborhood would be 7,500 through 12,500. And here we display the results of this attribute disclosure risk measure, where here the prior probability is approximately 1 over 11, and a higher probability indicates a higher risk. And we see that the two-phase synthesis depicted in orange is a little bit higher than 0.09, indicating that the two-phase has a slightly higher risk than that of the single phase. And we see a similar story here, where a higher ranking in this case is just a density frequency plot or histogram of the true income values, and a higher ranking here, i.e. closer to 1, indicates a higher risk. And again, depicted in orange, the two-phase synthesis shows that the two-phase did have a slightly higher attribute disclosure risk than that of the single phase. In summary, we found that the two-phase synthesis process had a much higher utility preservation than that of the single phase. However, this higher utility came at a price of slightly higher risk. And this trade-off between utility and risk is a well-demonstrated phenomenon in many applications. Some future work for this would be exploring additional predictor variables and Bayesian models, also non-Bayesian synthesis models such as classification and regression trees, as well as exploring additional data sets from the domain. So that concludes our presentation, everybody. Thank you for your time, and I hope you enjoyed it.